A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. You know, Herman, I was looking at some of the strike data coming out of the Middle East this morning, and I saw a report mentioning a standard deviation of 150 meters for a specific missile system. It struck me that most people reading that probably just glazed over the number. They see 150 meters, and they have no idea if that means the system is a precision instrument or a total disaster.
It is a classic problem. People love the average, the mean. They want to know the bottom line, number. But the mean without the standard deviation is like a map without a scale. You have the location, but you have no idea how much ground you are actually covering. By the way, before we dive into the weeds of variance, I should mention that today's episode of My Weird Prompts is powered by Google Gemini 3 Flash. I am Herman Poppleberry, and I have been waiting for a chance to do a proper statistics deep dive.
I knew you were excited because you put on your math vest this morning. Today's prompt from Daniel is about exactly this: how to actually interpret standard deviation in the real world. He specifically mentioned how people are encountering these terms while looking at war strike data from Iran, but he wants us to treat this as a broader statistics explainer. Because, let's be honest, whether it is missile accuracy, polling data, or how long it takes for your pizza to arrive, standard deviation is the secret sauce that tells you if the data is actually reliable.
Reliability is the perfect word for it. At its simplest level, standard deviation is just a measure of how spread out your data points are from the average. If I tell you the average temperature in a city is 25 degrees Celsius, that sounds pleasant. But if the standard deviation is 15 degrees, you might be looking at a place that swings between 10 and 40. The average is the same, but the lived experience is wildly different.
Right, so the mean tells you where the center of the dartboard is, but the standard deviation tells you how big the cluster of dots actually is. If the dots are all over the wall, you have a high standard deviation. If they are all Robin Hooding each other in the bullseye, it is low. But why do we use this specific math? Why not just say the range is 50 meters?
Because the range is incredibly sensitive to outliers. If one missile goes rogue and lands 3 miles away because of a software glitch, your range looks like a disaster even if every other strike was perfect. Standard deviation is more robust. It uses the square of the distance from the mean, which gives more weight to outliers than a simple average deviation would, but it still provides a much more stable picture of the typical spread.
Okay, so let's get into the how-to for the regular person. When someone sees a correlation figure or a data set, they usually look at the R value or the mean. How should they be looking at the standard deviation alongside those?
This is where most people trip up. If you are looking at a correlation, say between education level and income, the correlation coefficient tells you if there is a relationship. But the standard deviation of the residuals, basically the noise, around that relationship tells you how much you can actually trust that prediction for a single person. If the standard deviation is huge, the average relationship exists. But for you as an individual, the prediction is almost useless.
It is like saying, on average, people who eat kale live longer. But if the standard deviation is 20 years, eating kale might give you an extra day or an extra 4 decades. You just don't know.
Precisely. And we have to talk about the normal distribution here, because that is where the real magic of interpreting these numbers happens. In statistics, we have the 68-95-99.7 rule. It is often called the empirical rule.
I remember this from school, but give us the refresher. If I see that 150-meter standard deviation for a missile strike, what do those percentages actually translate to on the ground?
If the data follows a normal distribution, which most physical processes like wind resistance or mechanical jitter do, then about 68% of all strikes will fall within one standard deviation of the mean. So if the mean error is 500 meters and the standard deviation is 150, then 68% of those missiles are landing between 350 and 650 meters from the target.
Okay, so roughly 2/3 are in that inner circle. What about the rest? Because 2/3 doesn't sound very precise if you are trying to hit a specific building.
That is where the second tier comes in. Two standard deviations covers 95% of the data. So 95% of strikes would land within 300 meters of that mean, that is, 2 times 150. Then you go to 3 standard deviations and you are at 99.7%. In the world of high-stakes engineering, they often talk about 6 sigma. That is 6 standard deviations. If you have a process at 6 sigma, you are looking at 3.4 defects per million opportunities.
So when a company says they are Six Sigma, they aren't just using a buzzword. They are literally saying their standard deviation is so small that you have to go out 6 levels before you find a failure.
That is the goal. But in the context of the war data Daniel mentioned, seeing a high standard deviation tells you that the average accuracy the government is reporting might be a bit of a PR spin. If the mean is low but the standard deviation is high, it means they might hit the target perfectly once, but the next one might land in a vacant lot 2 blocks away. The lack of consistency is what the standard deviation reveals.
This seems like a good place to pivot to the high versus low discussion. We often assume low is good and high is bad. Is that always the case?
Not necessarily, though in performance metrics, we usually crave low standard deviation because it equals predictability. Think about pizza delivery. If restaurant A has an average delivery time of 30 minutes with a standard deviation of 2 minutes, you know exactly when to set the table. If restaurant B has an average of 25 minutes but a standard deviation of 15 minutes, they might get it to you in 10 minutes or it might take 45. Even though restaurant B is faster on average, most people prefer the slower but more predictable restaurant A.
I'm definitely a restaurant, a guy. I hate the any minute now window that lasts an hour. But what about a context where high standard deviation is actually what you want?
Think about genetic diversity or a stock portfolio. If every stock in your portfolio has the exact same movement, your standard deviation is low, but your risk is incredibly high because you aren't diversified. You want a variety of responses to market conditions. Or think about a classroom. If a teacher has a class where every student scores exactly 70%, the standard deviation is 0. That might look consistent, but it actually suggests the material isn't challenging the top students or the teacher isn't identifying different learning needs. A bit of spread can indicate a healthy range of individual expression.
That is a fair point. But back to the scary stuff, like the missile data. If I am looking at System A with a 50-meter SD and System B with a 200-meter SD, System A is clearly the better piece of tech, right?
From an engineering standpoint, yes. It means the manufacturing tolerances are tighter, the guidance software is more refined, and the external variables like wind are being compensated for more effectively. But here is the catch, and this leads into the common mistakes people make. People often confuse the standard deviation with the standard error.
Oh boy, here we go. What is the difference? Because I guarantee you 90% of people just heard those as the same thing.
It is a massive distinction. The standard deviation describes the spread of the actual data points, the actual missiles landing. The standard error describes how much uncertainty there is in our estimate of the mean. If you only look at 5 missile strikes, your standard error will be high because your sample size is small, even if the missiles themselves are very accurate. As you add more data points, the standard error shrinks because you become more confident in where the average actually is. But the standard deviation stays the same because it represents the physical reality of the system's jitter.
So, you can be very certain. Low standard error, that a system is wildly inaccurate. High standard deviation.
You nailed it. You could say, I am 99% sure that this missile system is going to miss by an average of 400 meters, give or take 300 meters. That is a low standard error of the mean, but a high standard deviation of the performance.
That is a terrifyingly precise way to be wrong. What are some other traps? I feel like people often look at these numbers and assume a normal distribution when it might not be one.
That is probably the biggest mistake in all of applied statistics. The 68, 95, 99 rule only works if the curve looks like a bell. But what if the data is bimodal? Imagine a missile system that either hits perfectly or, if the GPS fails, misses by exactly 2 kilometers. The average might be 1 kilometer, and the standard deviation might be huge, but almost no missiles actually land at the 1 kilometer mark. They are either at 0 or at 2,000.
Right, so the average is a place where no one actually lives. It is like the average. Human having one ovary and one testicle. It is statistically true, but practically non-existent.
When you see a standard deviation reported in the news, especially regarding complex things like war strike data or economic recovery, the reporter is almost always assuming a bell curve. But in war, you often have fat tails. This is a concept popularized by Nassim Taleb. It means that extreme events, the black swans, happen much more often than a normal distribution would predict.
So that 3 sigma event that is supposed to happen once in 1,000 times actually happens every Tuesday.
Precisely because the underlying system isn't a simple bell curve. If you are analyzing Iranian missile strikes, you might have mechanical failures, electronic warfare interference, or interceptors hitting them. Those aren't normal variations. They are distinct categories of failure that create a messy distribution. If you just report the standard deviation as a single number, you are hiding the most interesting parts of the story.
This is why I always get skeptical when I see these super clean mean accuracy stats. It feels like they are using the math to smooth over the chaos.
It is a form of data laundering. You take a chaotic reality, run it through a standard deviation formula, and out pops a clean, professional-looking number. Another mistake is forgetting that standard deviation has the same units as the mean. If the mean is in meters, the SD is in meters. If the mean is in dollars, the SD is in dollars. This sounds obvious, but it means you can't easily compare the spread of two different things unless you use something called the coefficient of variation.
Give me an example. Make it something I'd actually care about.
Okay, let's compare the accuracy of a long-range ballistic missile to a handheld grenade. A ballistic missile might have a mean error of 100 meters with a standard deviation of 20. A grenade might have a mean error of 2 meters with a standard deviation of 1. If you just look at the SD, the grenade looks more accurate because 1 is smaller than 20. But the missile's SD is only 20% of its total distance, while the grenade's SD is 50% of its distance. Relatively speaking, the missile is more consistent for its scale.
That is a great point. It is all about the relative scale. If I am a billionaire and I lose $1 million, that is a low standard deviation from my daily net worth. If I have $5 and I lose $1 million, I have bigger problems than statistics.
You would be a statistical impossibility at that point. But this really matters when people look at things like polling leads. You see a candidate is up by 4 points with a margin of error of 3 points. That margin of error is derived from the standard deviation and the sample size. If the standard deviation of the responses is high, meaning the population is deeply polarized and there are very few middle responses, that poll is a lot more brittle than one where everyone is hovering around the same opinion.
I want to go back to the practical takeaways for a second. If I'm scrolling through a news site or reading a technical report and I see standard deviation, what is the first question I should ask myself?
The very first question is, what does the distribution look like? Is this a bell curve, or is there something weird going on? If the author doesn't show you a histogram, a bar chart of the data, be wary. The second question is, how does this SD compare to the mean? If the SD is larger than the mean, you are dealing with a massive amount of noise. It means the average is almost meaningless because the data is so spread out.
It is like saying the average height in a room is 4 feet, but it is just a bunch of NBA players and a bunch of toddlers.
You would never find a 4-foot person in that room. Another thing to look for is outlier sensitivity. Ask yourself if a single catastrophic failure could be skewing that number. In the context of the Iran strike data, if 10 missiles hit on target and one lands in another country, that one outlier will balloon the standard deviation. A savvy analyst might report the median and the interquartile range, instead because those ignore the crazy outliers and tell you what the typical performance looks like.
It is funny how much truth you can hide with correct math. You aren't lying about the numbers. You are just choosing the lens that makes the picture look the way you want it to.
That is the essence of How to Lie with Statistics. But if you know what to look for, the standard deviation is actually your best friend for spotting those lies. It is the honesty metric. It tells you how much the person reporting the data is trying to hide the variance. If they refuse to give you the SD, they are almost certainly trying to sell you on a mean that isn't representative.
We should probably touch on how this relates to something like weather forecasting too, because that is a war we all deal with every day. When they say there is a 60% chance of rain, how does SD play in?
Weather models are essentially a bunch of different simulations run at once. They call it ensemble forecasting. If all 50 versions of the model say it will be between 20 and 22 degrees, the standard deviation is low, and the forecaster will speak with high confidence. If some models say it will be 10 degrees and others say 30, the standard deviation is high. A good weather app, though few do this, should show you that uncertainty cone. It is the same thing they use for hurricane paths. That cone of uncertainty is literally a visualization of standard deviation over time.
I love those cones. They're the most honest part of the news. It is basically the meteorologist saying, look, it is probably going to hit Miami, but it might hit Cancun. Don't sue me.
It is beautiful. It is a spatial representation of the 95% confidence interval. They are saying, we are 95% sure the eye of the storm will stay within this cone. As the storm gets closer and they get more data, the standard deviation of the model run shrinks and the cone narrows. It is a real-time reduction in variance.
So, to bring this back to Daniel's point about the strike data, if we are looking at these reports and we see a tight standard deviation, we can infer that the weapon system is high quality and the operators are well trained. If we see a loose or high SD, it might not mean the missile is bad. It could mean the conditions were chaotic, or the data we are getting is a mix of different types of strikes.
Or it could mean the defense systems were effective. If an interceptor hits a missile, it doesn't always vaporize it. Sometimes it just knocks it off course. That creates a miss that looks like a statistical outlier, increasing the standard deviation of the whole barrage. So, a high SD in an attack might actually be a measure of the success of the defense.
That is such a cool second-order effect. The noise in the attacker's data is the signal of the defender's success.
Statistics is all about perspective. What one person calls error, another calls evidence. We've talked a lot about the technical side, but I think the biggest takeaway for people is to stop treating the average as a single, solid point. Start seeing it as a fuzzy cloud. The standard deviation tells you how big and how thick that cloud is.
And if the cloud is big enough, you might want to bring an umbrella even if the average says it is sunny.
And that applies to your finances, your health, and how you read the news. If a study says the average person loses 10 pounds on this diet, look for the SD. If the SD is 15 pounds, some people gained weight. The average is a ghost.
I think we've given people enough to start being a real pain at dinner parties. Excuse me, but what was the standard deviation of that anecdote?
If anyone says that, I want them to email us at show@myweirdprompts.com. I will personally send them a gold star.
Or a very small, very precise dot. Before we wrap up, let's do the practical cheat sheet for when you're reading a report. Number 1, find the mean. Number 2, find the SD. Number 3, if the SD is more than half of the mean, be suspicious.
Number 4, check if they are assuming a normal distribution. Number 5, remember the 68, 95, 99 rule. If you are 3 SDs away from the mean, you are looking at something truly weird or a system that is failing.
And number 6, don't let the math intimidate you. It is just a way of measuring jiggles.
High-level mathematical jiggles.
Precisely. Wait, I almost said the forbidden word. I meant, you are right.
I'll allow it. It's been a long day of data crunching.
Well, this has been a blast. It is one of those topics that feels dry until you realize it is literally the fabric of how we understand everything from war to weather. Thanks as always to our producer, Hilbert Flumingtop, for keeping the standard deviation of our audio quality very, very low.
And a big thanks to Modal for providing the GPU credits that power this show and help us process all this jiggling data.
This has been My Weird Prompts. If you're enjoying the show, a quick review on your podcast app really helps us reach new listeners who might also be confused by missile strike statistics.
Or people who just like sloths and donkeys talking about math.
That is a very specific niche, Herman. I think the standard deviation of our audience's interests is probably pretty high.
And that is exactly how we like it.
See you next time.
Good job, teacher.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the close from sloth.